This is the first video in a two-part series dealing with molecular geometries. In this series, we will be looking at how we can go from a Lewis structure and using our electron geometries, determine the molecular geometries, particularly the types of bond angles and shapes that we expect to see in molecules. The first thing that we should note in dealing with molecular geometries is that the actual geometry, the molecular geometry, of the molecule may be different from what is predicted by the electron geometry, particularly when the electron groups are attached to atoms of different sizes, or when the bonding to one atom is different than the bonding to another, as is the case with a single versus a double bond. This will affect the molecular geometry around the central atom. Another thing that can affect our molecular geometries, particularly the bond angles, are the presence of lone pairs. So if we have electron groups that are lone pairs, that will affect the molecular geometry. Lone pair groups occupy space on the central atom, giving us an electron group, but are not seen as points on the molecular geometry. So by this, we mean that the lone pair occupies an electron group, but when we're looking at the molecular geometries, we're interested in where the atoms are placed in the molecules, not the electron groups. Because those lone pairs take up more space on the central atom, because their electron density is exclusively on the central atom rather than shared like it is in bonding groups, this can cause alterations in the bond angles that we will see. So the presence of lone pairs is going to affect the bond angles, making the bond angles typically smaller than is otherwise expected from the values in our electron geometry groups. Let's now look at the differences in our various types of electron groups and how these can affect the angles around them. Those types of electron groups include single bonds, double bonds, and triple bonds, as well as our lone pair electrons. Bonding electrons are shared between two atoms, so some of that negative charge that you would have from the central atom is removed or shared with its bonding pair. If you have this being your central atom, then the electrons are going to share a space in between the two nuclei. This causes the side that is away from our central atom to be constrained to a smaller region of space, which means that it will push the atoms around it less than if we had a lone pair. In the case of a lone pair, because the electrons are not being constrained by a nucleus on the other side, they're not being pulled or attracted to that nucleus, they can spread out, and this large amount of electron density causes the other atoms that are bound to the central atom to be pushed away from the lone pair. When we have double bonds, that is a stronger repulsive force than you see with a single bond because there are a lot more electrons in this particular space. But still, the lone pair of electrons pushes more. So the relative size of the repulsive force interaction of the various types of electron groups are as follows. If you have two lone pairs interacting with each other, this is the strongest repulsion force. So a lone pair to lone pair interaction is going to be the strongest repulsive force. They will try to push as far away from each other as possible. Lone pair to bonding pair, so that would be a lone pair of electrons interacting with a pair of bonding electrons somewhere else attached to the central atom, will have a stronger interaction than bonding pair to bonding pair, but a weaker interaction than lone pair to lone pair. And as a result, the weakest are going to be bonding pair to bonding pair. So if you have two things that are bound to the central atom, they will push against each other less than if one of the two things pushing was a lone pair. And that will push less than if both things interacting with each other were lone pairs. When there are three electron groups around a central atom, we have a trigonal planar electron geometry. There are times in which one of those three groups will be a lone pair. So when there are 3 electron groups around a central atom and one of them is a lone pair of electrons, the resulting shape of the molecule will be called a bent shape, sometimes referred to as a trigonal planar bent shape. The bonding angle that you'll find in this type of bent shape will be less than the 120 degrees that we typically find in a trigonal planar geometry. And this is because the lone pair takes up more space. So an example of one of these systems would be sulfur dioxide, SO2. The shape of SO2, we'd have a sulfur in the middle, an oxygen, and then a double bonded oxygen with a set of lone pair electrons on the top. And 6 electrons around that one and 2 electrons around that. So this will take up, because there are 3 electron groups, right? 1, 2, 3. This will have a trigonal planar electron geometry. Typically, trigonal planar geometries are going to have bond angles that are 120 degrees. But because you have a very large group of lone pair electrons up here occupying this very large circular orbital, that pushes your oxygen groups away from the lone pair. Because it's pushing the oxygen groups away from the lone pair, that will take our 120 degree angle and compress it. It will become less than 120 degrees. Expanding our consideration to 4 electron groups results in the tetrahedral electron geometry. If one of those groups, however, is a lone pair of electrons, then we have a situation when there are 4 electron groups around the central atom and one of them is a lone pair. The result is called a trigonal pyramidal shape because the pyramid has a triangle shape on the bottom and it is not lying flat within a plane. Instead, it makes a very shortened pyramid with the central atom located at the apex. Now, typically in a tetrahedral geometry, the angles are 109.5. So because we have a lone pair of electrons coming above our central atom, that lone pair has the greatest repulsion, so it is pushing the bonding groups down away from it, contracting the angle between them. So because this lone pair pushes down, pushes the hydrogens to go further away from it, that causes them to get closer together. So again, the shape that we have for something like ammonia would be trigonal pyramidal, and the angle is going to be less than 109.5. If we keep with 4 electron groups, but now change to 2 lone pairs, we get what we call a bent geometry. So when there are 4 electron groups around the central atom and 2 of them are lone pairs, the result is called a tetrahedral bent shape or just bent shape. It is planar because you have 3 different atoms. It, by necessity of geometry, has to fall within a plane. It looks very similar to the trigonal planar bent shape, except there's going to be a difference in the angle. The angle here is going to be smaller. In the case of the trigonal planar bent shape, the angle between the things that were bonded to the central atom were less than 120 degrees. In this case, because they start out at 109.5, if this was a perfect tetrahedral shape, and we now have 2 lone pair electrons which are pushing the hydrogens away from both of them, that will cause the hydrogens to, by necessity, move closer together. Because they move closer together, the angle between the hydrogen, oxygen, hydrogen will become smaller, making it less than 109.5. So again, you have tetrahedral electron geometry with 2 lone pairs is a bent shape. So to summarize for our tetrahedral, if there are no lone pairs of electrons, you have a regular tetrahedral geometry. So in this case, the electron geometry and the molecular geometry match. They are both tetrahedral. if we replace one of those bonding atoms with a lone pair of electrons, so going from something like methane to ammonia, we now have a situation where the angles are less than 109.5. In the case of ammonia, they're 107. This shape here is a trigonal pyramidal. There's a triangle on the base, and it makes a pyramid with the nitrogen at the apex. If we replace another one of our groups with another set of lone pair electrons, as we have in water, the angle contracts even more. In the case of water, the bonding angle between the hydrogen, oxygen, and hydrogen is 104.5 degrees. So as you can see, as we increase the number of lone pairs on that central atom, the bond contracts. It goes from 109.5 to 107 to 104.5.